This particular video episode, we're going to take a look at a unique type of bonding between metal atoms known as metallic bonding. Metallic bonding uses a type of structure where the metal atoms are essentially immersed in a sea of electrons, where these electrons are the valence electrons of the metal atoms that have been lost. The sea of electrons model is what allows for the unique properties we see in metals. One property of metals is that metals are referred to as something called malleable. Malleable means that something can be pounded or bent into a shape. Another property of metals is that metals are referred to as what we say ductile. Ductile means that a material can be stretched into a wire. Other properties of metals is that metals conduct electricity. They also conduct heat very readily, and metals are also shiny. These would all be the conduction of electricity, being able to conduct heat readily, and being shiny are additional properties of metals that are unique to metals because of the sea of electrons bonding structure that holds metal atoms together. Taking a look at a couple of metal atoms, in this case we have a sodium atom and another sodium atom. Metals readily lose electrons. In fact, they want to lose their valence electrons. So this single valence electron out here in this sodium, it wants to lose that electron, and this sodium also wants to lose that electron. By losing an electron, each of these sodium atoms has become a 1+ ion. And they also have a full valence shell of electrons, which makes both of these sodium atoms very happy. What happens next is the sodium, because it's a 1+, will readily pick up and gain this electron that's been tossed from a neighboring metal. Then immediately upon picking up the electron, the sodium atom now wants to get rid of it again and just tosses it right back to another sodium atom that's in the vicinity. So we end up getting these electrons tossed from one atom to the other and back again, back and forth. The electrons keep going from one atom to another atom within the metal atoms. It's almost as if the atoms are playing a little bit of game of hot potato, as they just take that electron and toss it from one side and then return it to the other side and just keep going back and forth and back and forth and back and forth. This allows the nuclei of the metal atoms to be immersed within this mobile sea of electrons that are continually being tossed back and forth between the metal atoms. So what we end up with, for example, with the alkali metals, or here the alkali earth metals are typically +2, is the valence electrons get lost and are getting tossed amongst here, there, and everywhere within the nuclei of the atoms. So these electrons getting tossed from one atom to another, and then the nuclei, positively charged now ions of the atoms, metal atoms that remain, are immersed in this negative sea of electrons. It's the positive and negative interaction that electrostatically holds everything together, and that creates our metallic bond. The sea of electrons gives metals their many properties. Let's say, for example, we were to swing quickly down and strike the metal with a hammer. What happens is, because the electrons are mobile and moving hither and there amongst the positive nuclei remaining of the atoms, is this atom can just shift downward, pushing this one down, without causing any type of fracture from one atom to the other. This allows something where you pound a metal for the shape to actually be created by hitting it and pounding it, rather than having the metal fracture or break. And that's because these atoms can readily move amongst these loosely held electrons that are getting tossed back and forth between the nuclei of the metal atoms. Now, for a material to conduct electricity, we have to keep in mind that electric current is the flow of electrons. Now, because the electrons here in the sea of electrons are loosely held and thus being tossed back and forth from one atom to another, the electrons can readily move between the atoms. So if we have some input of energy, begins to push the electrons thus move readily through the metal atoms, and we get this movement of electrons, which is electric current, which is why metals can readily conduct electricity. Another feature of metals is they can readily conduct heat, and it's also tied to these loosely held electrons. That what can happen is heat is a transfer of kinetic energy. These electrons with their kinetic energy bump from one into another, and the kinetic energy gets transferred through the metal. So the heat will readily flow through the metal as the electrons can readily jostle and move and bump into one another. And it allows for movement of heat through a metal, whereas another material that has tightly held electrons would be unable to transfer the heat so readily as the metals can with their loosely held electrons in the sea of electrons model. We have another type of bonding to look at, or structures. It's materials that are known as network covalent solids. Network covalent solids are materials that have all covalent bonds, and it's predominantly with the atoms carbon and silicon are our network covalent solids. There's only 3 network covalent solids we're going to key in on here. There's 2 forms of carbon that are network covalent solids, diamond and graphite, and there's 1 for silicon, which is quartz, also just plain old sand. This is silicon SiO2. Let's first take a look at the 2 types of carbon, but you're going to focus mainly on these. We have diamond and we have graphite. Now, the thing about a network covalent solid is there's no individual molecules. This is a carbon atom covalently bonded to another carbon atom, which is covalently bonded to another carbon atom. And this keeps repeating and repeating over and over and over again in 3 dimensions. So it's carbon atoms tetrahedrally bonded covalently to other carbon atoms in a very rigid and strong 3-dimensional structure. This would be diamond. Now in diamond, because each carbon atom has a tetrahedral shape surrounding it 3-dimensionally, the hybridization of every carbon atom in diamond is sp3. Graphite, on the other hand, is also carbon atoms covalently bonded to neighboring carbon atoms. But the difference is with graphite is the carbon atoms are sp2 hybridized. So we end up with this very flat structure that's only a single atom thick, where we have these hexagonal shapes of carbons covalently bonded, covalently bonded, covalently bonded to one another, and it keeps repeating and repeating and repeating, and we get a large sheet of carbon atoms, which is right next to another large sheet of carbon atoms. The thing is, we don't have any individual molecules in graphite, similar to as we see in diamond. For a moment, let's consider something such as water. Now, water is made up of individual molecules, where we have an H2O with the water molecules having covalent bonds inside here joining the oxygen to the hydrogen. So we have these independent molecules made up of 2 H's and an O. What holds one water molecule to another is the hydrogen bond, this connection between water molecules. In a material such as water, when we melt it or when we vaporize it and turn it into steam, all we're doing is severing these hydrogen bonds that exist between neighboring molecules. That's why water melts at 0 and why we can turn it into vapor at 100 degrees Celsius. A network covalent solid, on the other hand, something such as diamond, all the carbon atoms are covalently bonded from one atom to another atom. There isn't any beginning or end of a molecule. We lack dispersion forces or dipole-dipole or hydrogen bonds. In order to make something like diamond melt, we actually have to break and sever the covalent bonds that connect one carbon atom to another carbon atom. This be one reason why we see such an extraordinarily high melting point just to turn the solid to liquid for diamond. It's at 3,500 degrees Celsius because it takes so much energy to actually break and sever the covalent bonds that connect one atom to another within a network covalent solid. Graphite, another network covalent solid, with the flat sheets of carbon atoms. From one sheet to another, all that exists in between these sheets of carbons are dispersion forces. This is why graphite makes such an excellent lubricant, because one sheet of carbon atoms can just readily slide over another sheet of carbon atoms. And this ability of the sheets of carbon atoms to slide over one another makes graphite an excellent lubricant. Another feature of the network covalent solid graphite, because all the carbons are sp2 hybridized, we have a p orbital that's not part of the hybrid scheme. What this allows for all these p orbitals on the carbon atoms is that we get delocalization of electrons. And these electrons, which go through essentially what are some pi bonds, is because the electrons can drift from one unhybridized p orbital to another, is that graphite made of carbon, even though carbon is a nonmetal, graphite has the ability to conduct electricity. Because of these electrons, it can readily move in the p orbitals that are perpendicular to the bonding plane. We get the electrons can move, and movement of electrons is flow of electricity. This gives graphite some of its unique properties as a network covalent solid.